This video introduces OATH, an adaptive obstacle-aware task assignment and planning framework for heterogeneous robot teaming. Multi-robot system has attracted growing attention but remains challenging in obstacle-rich environments. In our work, we focus on a team of heterogeneous robots, including drones and ground robots, that need to complete multiple pickup and delivery tasks in an environment with known obstacles like walls and unknown obstacles like iron doors and bushes. To solve this problem, we design a hierarchical framework called OATH. It mainly has 3 stages. First, we do environment and map preprocessing. We develop an adaptive halt and sequence map, which adjusts the density of sampling points based on how complex the environment is. In open areas, we use fewer points, while in regions with many obstacles, we use more points. This gives us a more accurate map without increasing computation too much. Then we compute Dijkstra distances between every pair of tasks, which will later be used for task assignment. The second part of our framework is heterogeneous task assignment. Here we perform a hierarchical process. We first cluster tasks using the obstacle-aware distances. Then, robots join an auction process where each one bids for the cluster that matches its capability and is close to its position. After a robot wins a cluster, it selects the specific tasks to execute by solving a mixed-integer linear program. This design helps each robot get tasks that fit its capabilities and location while keeping the overall plan efficient. The third part is dynamic path planning. We use an algorithm called LTLD*, which allows a robot to replan its path dynamically whenever it encounters unknown obstacles. Once a robot finishes its current set of tasks, it goes back to the cluster auction selection loop and continues until all tasks are done. In addition, our framework leverages a large language model to interpret human instructions and directly guide the planner in real time. Here we show task assignment results for task type numbers equal to 2, 3, and 5. The assignments strictly follow the robot's capability constraints. When the nearest cluster includes task types that a robot cannot handle, it does not choose that cluster. Instead, it selects a more distant but feasible one. For example, in the task type equal to 5 case, Robot 1 chooses a farther cluster because it matches its handling capabilities. This shows that our assignment strategy respects both capability and spatial efficiency. In our experiments using the Isaac Sim simulator, we test with 2 ground robots and 2 drones. Ground robots can handle both red and blue tasks, while drones can only complete blue ones. During the simulation, you can see that the ground robots tend to first finish the red tasks before switching to blue tasks, which matches their capabilities perfectly. Finally, we also test the LLM-guided planner. When we add a new special task, one ground robot immediately changes its plan and takes that new task, since drones cannot complete the special task. When a new obstacle is detected, it is added to the current map, so later robots will automatically avoid it without wasting time exploring. And when a task is set to higher priority, every robot updates its bidding score to first bid on it after finishing their current work. In conclusion, OATH provides an obstacle-aware and scalable framework for task assignment and planning in heterogeneous robot teams. By combining adaptive halt and map sampling, hierarchical task assignment framework, and dynamic replanning with LLM guidance, OATH improves both efficiency and adaptability compared with state-of-the-art methods. Thank you.